focus on is laboratory experimentation. And this has some nice benefits. One of the things you can do in a lab that you can't do on the real internet is have repeatable controlled experiments. And this is nice, say, if you're trying to develop some new network protocol and you want to make sure it's really thoroughly tested, but you don't want to just release it into the wild and see what happens, right? So you can basically generate some traffic on a few machines and test your protocol and see what performance looks like, and do that a few times, and that's better and often easier than trying to build some analytical model to do this or perform for measurement. And the key here is to do this in a realistic way so that the results you have actually mean something on the real internet. And so you want to use for the traffic that you generate, say, network traffic that was captured from the real internet, a real network trace. And you want to accurately replay those traces. And this is like a non-trivial problem, right? Because you can't just replay the individual packets that you see going across the wire because of the congestion control mechanisms in TCP, which is a widely deployed protocol on the internet. Behaviors are adaptive to the state of the network condition. And so you want to be able to talk about them at a higher level that's network independent. And so I'm going to talk about some ways to do that in a little bit. And so if you don't have a good experimental design, then you get garbage and Oscar. So let's talk about scaling network traffic. This would be a really nice thing to be able to do if you had a method that could realistically scale network traffic, and do so in a way where if you had some input network trace that had some interesting properties, and you want to see what happens if traffic volume increases by 30%. What happens to these other properties as well. And this would be a really useful thing for both researchers and network administrators to be able to do. I'm sure UNC ITS would like to know how their network infrastructure is going to perform if enrollment's going to go up by 20% next year, for instance. And if there were a good way to artificially scale traffic, we could do this much. They could take traffic that's currently on the network, blow it up, and see what happens to their infrastructure. And so I kind of am quasi-formally stating this offered load scaling problem, where basically you have some input traffic and you want to adjust the offered load, which is the number of bytes transferred across in this trace you have over its duration, and do so in such a way that the other properties of it are maintained. So let's talk about a model for talking about this. Is the ABT model. Teamix, a traffic generator for actually performing these experiments, and block resampling, which is a particular approach to performing this traffic scaling. So ABT model is a way of thinking about TCP connections. It was developed here at UNC. It basically models a single TCP connection as a series of one or more request-response sequences separated by some quiet period known as a think time. And so we represent each of these request-response think time sequences is known as an epoch, and a connection vector consists of one or more epochs. And it has a structure kind of what's shown here. You can have a caller, which would say you sitting at your web browser, and a callee, which would be CNN.com, for instance. And this A1 is going to be you loading up the CNN.com web page or sending the request for that. And B1 is going to be the server sending something back. Then you imagine you're going to sit there reading links and clicking on something else before you send your next request. This all happens in the space of one connection. So now that if we take this model of connection structure, we can use that to generate synthetic traffic. And basically what we do is there's another tool here developed here at UNC called Teamix, which is a system for creating empirically derived connection vectors. And what that basically means is that you can capture a network trace, and we have here an anonymized packet header trace, and do some processing and turn that into a set of connection vectors that model high-level network-independent behavior of that trace. And then to actually perform your experiment, you'll split it up into a bunch of machines that are separated by a couple routers, for instance, and you'll stick a monitor in between, and you can monitor the traffic that's going across in the same way that you originally captured that anonymized packet trace from some other network. And then your results should approximately match what your original input trace was looking like. So that brings us to the question of once we have one of these sets of connection vectors and we want to change the load on it, how do we go about scaling it? So an approach that was proposed by a graduate student here a couple of years ago, it's now called, I refer to it as randomized block resampling. And so this graph, even though it consists of blocks, it is different than the previous block graph earlier, but it represents a set of connection vectors, right? And each one of these represents a single connection. And you can imagine this set of connection vectors has some duration d, a offered load, which is the total number of bytes transferred over that duration of L, some number, hundreds of megabytes, or megabits per second, excuse me. And so what we'll do in this block resampling is we define something called a block duration, and we split our connection into a set of blocks. And each of our, depending on the start time of each of these connections, each connection vector falls into a specific block. What we want to do is we want to take this and transform it into a new set of connection vectors with some target load of L prime and a target duration of D prime. And so here's what we do to do that. We allocate, our second set of bins down here below that are empty, and we have our original trace. And basically what we're going to do is we're going to randomly allocate blocks from our original connection to blocks in what we want our new resample trace to be. And this is done, blocks are selected uniformly at random, and it's selected with replacement. So while I don't show it here, one block could be used to fill every block in the resultant trace. And this might happen multiple times if you want to, inflate the offered load of your connection by several multiples of your original offered load. Finally, to actually achieve what your desired L prime will be, is you're going to add, again, uniformly at random, individual connections to this resultant trace until you have approximately your offered load. And so getting back to a higher level, the goal here, is to understand what happens when more traffic is added to a network and do that in a realistic way. And what we'd like to do, ideally, is unleash more users into the wild and let them run amok and see what they do. But that's not practical to do in any repeatable, controlled way, or perhaps ethical way. But what we can do is something like block resampling, and it's a relatively straightforward process. We're just selecting connections and moving them around. And the scaling of offered load itself is not really that hard. But what it means to actually scale network traffic is a poorly defined concept. And when we scale a first order measure like offered load, it affects second order measures such as what behavior queue links, for instance, that you're gonna see on your routers. And so kind of one way to think about this would be like, say I told you to increase the size of Citizen Hall by 15%. And there are a few ways that you could do this. One, you could make everything proportionally 15% bigger, or you could make a bigger lobby and leave everything else relatively the same, or you could tack a new building onto it. All these are different approaches to increasing the size, and they all meet that primary correctness condition of scaling the offered load, but the underlying meaning of that is something different. So what I did is I did some experiments to explore kind of what these second order effects are when you scale a trace using block resampling. And so as I described earlier, we captured a trace from a Fortune 100 companies network in 2006, and basically used this trace as the synthetic traffic with which I was going to scale to perform my experiments. Some just descriptive statistics here. I used 1 hour of this trace. It contained, during that hour, we saw 2.7 million connections, and the offered load was almost exactly 400 megabits per second in the high direction. The round trip time per epoch, the latency, if you will, the mean was 92.3 milliseconds. Each connection had the mean of 8.8 epochs, and connection size, the average connection size was 192 kilobytes. And each of those last three, the last two rather, the lengths of connections and the size of connections really are very long tail, have a very long tail distribution, as you can tell from their standard deviations. To actually perform these experiments, I used the NetLab testbed here at UNC. It's set up as the network topology is like a dumbbell that represents a peering point between two internet service providers, representing where two of these, large networks connect to each other. Basically, we have 30 pairs of physical systems as end systems that are running the traffic generator Teamix, which are replaying this set of input connection vectors. It's connected by two software routers that in between them is a bottleneck link for the network of 1 gigabit per second. And for these experiments, I artificially constrained that link such that the offered load of the trace is 95% of the available link speed. So in this case, the bandwidth cap was 424 megabits per second. There are a couple points in which we monitor the experiment. One is right in between these two routers, and another is in between one pair of end systems and one router, so we can get information about packet arrivals at the queue. And actually, there are a bunch of points where we monitor this whole experiment because each end system is performing its own monitoring, and each router is performing logging data as well. So basically, what I did next is to kind of understand what variability is introduced in some second-order measures for block resampling. I essentially took this original set of connection vectors that was already at 400 megabits per second, and I block resampled it using the technique I described earlier back to 400 megabits per second, using a block size of 30 seconds, and I generated 1 hour traces. And because block resampling essentially rebuilds a set of connection vectors from scratch, this allowed me to make a kind of apples-to-apples comparison from the original set of connection vectors to these new block resampled ones. And so this chart right here is a throughput comparison, and the colors are a bit faded out here, but those squares at the top basically represent the throughput from the original set of connection vectors. And so pretty much the throughput during almost the entire duration of the experiment, except for the last 20 minutes or so, was at the link capacity. So that meant there was congestion present in the network. Whereas the purple, blue, and green lines represent 3 instances of block resampled connections, all to 400 megabits per second. And as you can see, the actual throughput time series for each of these is wildly different. Some of them don't even reach the congestion point of 424 megabits per second, even though these were all block resampled with the same set of input parameters and the same input connection vectors. So a more dramatic difference is seen when you look at the number of active connections in an experiment. What that basically means is a connection is considered active if its connection vector has more data to send. And so you can imagine you're sitting in a think time with no data being sent, but the connection's still active. And so in the original set of connection vectors, we have this really nice, smooth growth and decline of active connections in our replay. Whereas in all of the block resample connections, orders of order of 20 to 40,000 fewer, or rather 40 to 60,000 fewer connections at any given point in the replay. And so there's obviously some really huge variation in the number of connections that are actually being replayed at any given point in a block resampled set of connection vectors. So this is impacts for queue length, which is a really important performance metric for TCP protocols, or variants of TCP, for instance. And the red line again is the length of the queues at the routers for the original set of connection vectors. And basically, what we see here is, again, for the first half of the experiment, we see there's a pretty good degree of congestion on the networks. The queues are full, and it only empties out towards the very end of the connection of the experiment. Whereas for all the block resampled traces, we have a completely different pattern of queue length favor. So one of these, for instance, has 3 spikes in congestion. The rest of the time, there was no congestion whatsoever. And this is not reflective of what we saw in our original set of connection vectors, and arguably not a truly realistic replay. Again, this is the cumulative distribution function of basically Q length, and what this means is that at 50% of the time, each of these experiments contained, one of the block resample one contained 136 packets in the queue, the median, and the original contained over 2,600 packets in the queue. Whereas, if you look at the other two block resample connections, it's again very different distributions. So seeing this, it begs the question, how would you modify block resampling to generate more, to make these second order measurements more accurately match what you originally saw? And so one of the original goals of block resampling was to be able to introduce variability into an experiment. So if you have a single set of connection vectors that you want to run a bunch of different experiments with, it'd be nice to be able to create new ones that are different but also kind of the same at these second order level, these second order performance measures. And so the way this is done is by randomizing the set of connection vectors that you have before you do the scaling to achieve your desired load. So my hypothesis was that if you take this out, then you're going to get some more accurate second order performance measures. And so what basically will happen is you'll get a set of connection vectors which look a lot more like your original set, and rather than randomly reassigning blocks, we only perform from that scaling by uniformly selecting connections and adding them back to the trace. So to test this, I basically created another set of connection vectors. I took the original set of connection vectors, I artificially scaled it down by removing 10% of the connections that were originally present in that trace. And then using that baseline, I block resampled that back up to the original offered load of 400 megabits per second from about 350 for each of these. Each of the bases had slightly different original load. And I did this with both the randomized block resampling technique and then the block resampling technique I just described, which I refer to as a self-block resampled, which doesn't have the random reallocation of blocks. And you see this cluster of, this is again active connections. For the top lines right there represent the original set of connection vectors, as well as the 3 self-block resampled replays, which match the number of active connections much better. And once again, the random block resampled ones are still showing about half the number of active connections at any given point in the replay. And so once again, there's a significant effect on Q length here, and here's a time series of one of this particular set of experiments. The red line is once again the original, and the blue represents a self-block resampled experiment. So I performed it. There was one of these actually had a queuing that looked relatively similar to the original set of the original Q-link behavior that we saw from this first set of connection vectors, in that there's a large spike in congestion towards the beginning of the experiment and then a gradual decay throughout the rest of the experiment. But if you look back at that active connections graph, at around the 12-minute mark when we see all those connections, the number of active connections for this particular replay jumped from 20,000 to 40,000, which is not something you'd expect to see on the real, a real corporate network. All of a sudden, twice as much traffic is being shot back. So that's not a realistic replay, we would argue. So the logical question is why is this happening? And I'll cut to this chase and say I'm still not entirely sure why it's going on, but we can look at rule out, I suppose, some possible reasons for this. And the logical thing is, if you have 2 sets of connection vectors and they both have the same average offered load, then you'd expect that there would be some difference in the distribution of either the durations of these connections that you're replaying, assuming that there's a difference in active connections, There'd be a difference in the size of the length of these connections you're replaying, or there'd be a difference in the amount of bytes the distribution in the sizes of these connections in terms of number of bytes they transmit. And this turns out not really to be the case. For the connection duration distribution, there's not really an appreciable difference between either the randomized block resample, self-block resample, or really the original set of connection vectors. This is on a linear scale, I'll note, and the median connection durations you can see there, 343 for the randomized block resample, about the same for the self-block resample, and only around 780 for the original. Looking at connection vector sizes, this is pretty much representative of all the experiments that I sets of connection vectors I generated. The distribution is essentially the same for all of them. Any variation is easily explainable by the random selection of connection vectors for the small amount of scaling that was needing to be done. So that's basically the analysis I performed. Some future directions for this is trying to really identify what the causes for this discrepancy would be. Like I said, I don't really have any evidence that points to one explanation or another very strongly. But there are a couple other measures like this that I was able to rule out that I'm not going to discuss today. But one thing that is a bit suspect is that when you're performing the original block resampling, right, the allocation of connections into bins is only dependent on their start time. And if you take, say, a connection that lasts for 10 minutes, for instance, and you stick it in that first block, and your block duration is only 30 seconds, it's going to span multiple blocks, right? And block resampling doesn't take that into account at all. And so what the result of this, I believe, is that when you're actually replaying these connections, performing the experiments, one of the measures you get back is number of incomplete connections. Presumably, if you're running an experiment, when the machine dies, all the connections it was supposed to generate aren't going to get run. So it's a measure like that. But all the traces that were randomized block resampled had substantially higher numbers of incomplete connections. The original had around 600, and usually I'd see an order of 10,000s to 50,000s of incomplete connections for the block resampled. It would also be also talking about improvements to the block resampling technique would be interesting to, rather than looking at the average load, the offered load for the entire duration of the trace, look at per block and try to get each block to actually match the throughput or your desired throughput. And this would again require taking into account the end times of connections. So my conclusions is that block resampling, as it stands, introduces significant variation in trace replays. You saw all these things. About half the number of active connections at any given point. Significant variation in Q-length distributions. The throughput will jump around, doesn't stay reflect what you saw in the original connection or original set of connection vectors. Using the self-block resampling reduces this variation, but you lose your ability to introduce controlled variation into the experiment, which arguably you never really had before, but it doesn't even get rid of all the variation, so it's not really the full answer, and it's still unclear why this is occurring, and I guess fundamentally scaling a network traffic is not as simple as it might seem at first. So some quick acknowledgements. Thank you, Dr. Fay, for support. Soon to be Dr. Jayakat for assistance and mentorship for all this, and Dr. Felix Hernandez Campos for his wonderful dissertation that inspired this work. So I guess I'll take questions now.
Thank you. Questions for Shadi? So I'll ask one. So do you think that this issue of the connections of not taking in end times into effect would be, is another possible way to do this that the experiments just weren't running long enough?
Right.
Or duration was just too short?
Yeah, that's certainly also a possibility. I think that their behaviors in these traces that you see, that like diurnal effects and the usage across the day, like after lunch, people use the internet a lot at work, right? And so there are these kind of variations that you see from the original source traces and so forth, which an hour may not be long enough to really capture all of that. I think that also the fact that a lot of these connections, we had several connections that lasted from the beginning of the trace all the way up to the end. And they were actually artificially cut off and started because they started before the trace began and ended after it ended. So I think that that would definitely be a good thing to do. Yeah.
In the experiments you reported, you were sampling and maintaining the number of connections and also the data volume. So I guess my question is, when you resample, do you want to scale the number of connections or the
only the basically all that you're doing is scaling the total number of bytes transferred, such that the average load with that number of bytes transferred in your target duration will equal your target load.
So different connections correspond to very different sizes.
Exactly, yeah. And
you're sampling them uniformly?
Correct, yeah. And so that, it seems that I think that's still a valid way to go about doing things, right? Because you're essentially, it's hard to know if you were to the overall goal, right, is to simulate what adding users to the network would look like. And so it's not really fair to bias one way or the other for these connections, connection sizes towards smaller connections or larger connections or anything like that without knowing what adding users would look like, right? Because any of these connections could be added by your hypothetical added users.
In your analogy of the building, it's you have big rooms and little rooms,
right?
And you just pick room random. But if you pick big rooms, you add a lot to the building.
Right, but I mean at the same time though, like at the end of the day, you're still transmitting the same number of bytes over the entire length of the connection, the length of the trace. And so I think that it would be an interesting thing to consider, but I haven't really looked into that enough to know. Yeah.
Well, let's thank Shadi again. Thank you. Our second speaker will be Maggie Zhou, who will tell us about her work on virtual percussion instruments.
So, hi, my name's Maggie. I feel like I know everybody in this room. There's only a few strange faces, which will be nice. A little bit more casual that way, maybe. So I'm going to talk to you about the work I've been doing for roughly the past year. And as Dr. Jaffe just said, it's on virtual percussion instruments on touch-enabled surfaces. So up there, just to give you a preview, that's a multi-touch table that is currently living upstairs in the G Lab. Am I talking at a reasonable level before I keep going? Okay, cool. So I'm going to start with a very, very brief history of musical instruments, very incomplete as well, and try to motivate the work that I've been working on a bit and give you the main idea and the sense of things. And then I'm going to give you a bit of background on sound synthesis, which is one of the tools we used in our work. And then I'm going to give you some implementation details, show you a longer demo than the one you just accidentally heard, and then go over a very small preliminary user study I did about a month ago, as well as talk about some future ideas I have for this work. So to begin, we have, I guess, 6 different types of instruments of various forms. So these spread from a harpsichord, which is in the top left-hand corner, very old Baroque 16th century to 17th century, to down here we have, it looks kind of red, and this is a tool almost that musicians can use to plug into their digital instruments to control the frequency that comes out of it. So if you wanted to do some sort of distortion effect. Similarly, also contemporary, sort of, we have this purple pedal in the, I guess, your right-hand corner. And it makes the wah, wah, wah sound. So the point of this slide is to show you, first of all, how much instruments have changed in the last few centuries or so, but also, I guess, sort of an example of how much technology has been integrated into music, especially recently. And another example of that is the Rock Band set that we have up there. How many people have played Rock Band or Guitar Hero? Like everybody? Okay. Cool. So the work I'm doing is slightly different than that, and I'll get into why that is so, I guess, now. So the type of Rock Band and Guitar Hero was a lot of the motivation behind this work. There's been recent attempts at digital musical instruments from novel hardware standpoint. So the Guitar Hero guitar is not a real guitar, as anybody who likes to pretend to play the guitar will tell you when they play the video game with you, as well as just from a more research standpoint, new tools for creating music on the computer. So an example of this is Max SMP, which a lot of composers like to use to create sound on the computer. So there's a lot of disadvantages to it. So when it comes down to it, the computer is not a musical instrument. It's a computer, there's a keyboard attached, and it's not an intuitive way of writing or creating music. Similarly, nobody's going to be playing guitar for a show or for their band based on the Guitar Hero guitar. There's a lot of disadvantages from the novel hardware. Additionally, but on the other hand, the advantage of it is that you get the flexibility of the digital sound. So with Max MSP, which I just mentioned, you can create different sounds that you wouldn't necessarily be able to create with physical instruments unless you had tons of them, unless you had hundreds of them spread out through the room. And you can also change things on the fly really quickly. So the motivation of our work was really to get rid of the disadvantages while maintaining the advantages. So let's see if this will play. Okay, so here in this clip, you just saw a user play what looks like a xylophone on a piece of hardware that doesn't look like a xylophone if you've ever seen one in real life, but sounds pretty close to one. And you can see that our mallets are pretty similar to what mallets on a real life xylophone look like if you've seen one before. And Zamin, who's the one playing, has told me that she doesn't play any music at all, but this was a pretty quick way for her to get up to speed and to play a little piece of music like this. So I guess, let's see. The main contribution of our work is to get the flexibility of digital musical instruments, which are a lot, without forcing musicians and new users who aren't necessarily musicians to learn new gestures or to learn new hardware in order to play the music. So you take the traditional gestures that you would use to play the normal instrument, but you get all the benefits of a digital instrument. So the benefits of a digital instrument, to go to that a little bit more in detail, are changing the physical parameters. So you can have different types. You can have different types of xylophones. You could have one that's made out of metal or one that's made out of wood, for instance. In addition, you can have multiple instruments on the same piece of hardware. Just briefly, I'll go more into that in a second. So we did this by combining physically based sound synthesis with touch-enabled hardware. And I think I already said all this, so I'm not going to say it again. This is the pipeline of how our software works. And I'm going to go through each module step by step, and then I'm going to pause and ask her questions about everything I've covered so far before I move on. So we implemented this both on graphical tablets, which are things that artists use, and a multi-touch table. So regardless of how the instrument, what the instrument is, you have user input, you have the user touching the instrument. And from this, we have a physics engine which collects the interaction on the tablet and takes it and tells the sound synthesis module, this is where the impulses are. This is how the user interacted with the tablet. This is how the user interacted with the table. And the sound synthesis module then takes that information, which is anywhere from how fast it was touching, the force touching it, as well as the location of the touch, and produces sound based on a series of parameters that's also in the sound synthesis module. Okay, I'm going to pause. Questions? Does this...
What does the table measure?
I'm sorry?
What does the table measure?
Okay, the table uses direct illumination in order to get the touches. So it measures the location and also how big the touch is. So if I use my whole hand versus just using one finger, it'll say that you had a greater impact force, so it'll produce a larger sound. That's how we're handling the...
Is it linear with area?
I'm sorry?
Is it linear with contact area?
I'm actually I'm actually not sure. I don't know how it determines, I don't know how the API determines the difference in contact area, and we're just handling based on a measurement it gives back to us. And I get a bit more into the hardware in a second. Any other questions? Great. So I'm going to go a little bit into sound synthesis and how it works, because that's an important part of how the whole system works. So I guess the main takeaway point for the sound synthesis section is that it's physically based sound synthesis and not pre-recorded sounds. So a lot of digital devices or electronic instruments, what they'll do is they'll have pre-recorded sounds. So sometime when someone's creating the hardware, creating the instrument, they went out and recorded a piano, or they went out and recorded a guitar, or recorded someone hitting a cymbal, and then they play back the same sound each time. With physically based sound synthesis, each time you play a note, each time you try to play the instrument, it creates a new sound based on a series of, based on how you hit it and the location of how you hit it and the materials that you've told it has. So this is basically embedded inside the sound synthesis module I showed you earlier in the software pipeline. And what it does is it takes in the impulses, which is the location and the pressure of where you hit it, and then using the modes it has inside based on the parameters of the material, it then creates sound. And so the three main benefits of sound synthesis are the fact that you can change the materials, the sound changes based on where you hit it on the instrument, and the sound also changes based on how hard you hit it. And so I have a few video clips demonstrating that. So this one is changing materials, if I can manage to click on it. There we go. So this is a wood xylophone. And this is a metal. So it's the same interface for the user, but you get a very different sound based on just changing the materials. And ideally, what we'd like to be able to do in the future is have a set of materials that the user can choose from, say metal, wood, brick, and then they can change the materials and play a slightly different sound.
When it's hit in the middle, it sounds like this.
Forgot to unclip it. So the beginning part of that clip showed showed the drum being hit on the side, and then the end showed it being hit in the middle. And then finally, how forcefully you hit it also changes how loud the sound is. So, briefly, a lot of these parameters would be fairly straightforward to change. Just in a typical electric device, you can change the amplitude of the sound without necessarily having a really complicated physics engine like we did. However, we can change so many more parameters than just the sound, and also you can change the modes to model the materials, which is something you don't get just by messing with the frequencies inside typical electric instruments. So now I'm going to go into implementation details about the tablets, the graphic tablets, and the multi-touch table, which were the two pieces of hardware we implemented this on. Before I do that, are there any questions about sound synthesis and why it's a good thing?
Did you change the sound depending on how long the mallet stayed in contact with the
So we actually did that for the graphics tablets that we implemented because the way the API gave us information, we were able to keep track of the duration in an optimal way. But the problem with the multi-touch table is that when we tried to do that, it ended up slowing down our code significantly so that the user experienced serious lag when they were playing the instrument. And also, the main instrument we implemented for the multi-touch table was a xylophone. And when you hit a xylophone, the sound doesn't change that much depending on the duration of your contact. It just is dampened a little. Because it's a percussion instrument and because the sound is produced upon
right
hit.
much if you leave the mallet on?
I'm sorry?
Isn't it dampened right much if you leave?
I think on a typical metal bar xylophone, yes, but not on the marimba, which is the one with the tubes. Yeah. So I think it would have been better if we had kept track of, say, maybe after a certain duration of touch, you dampen the sound significantly. That would have been better than not keeping track of it at all, and that would have been probably not too code complicated to slow down the process.
Have you examined how closely your synthesized sounds match the overtones of real instruments?
So the overtones are actually tricky. So the answer is no. And a lot of the sound synthesis work was done by Jameen and not me. She's currently working on integrating modal analysis in a way that makes the frequencies match up in an automatic way. And the way we tuned these xylophones and these drums was by ear. So it's very likely that these overtones don't match up very well at all, which I'm sure you recognize, and this is why you asked that in the demo.
You have waveforms.
Mm-hmm.
You could compare waveforms.
Yeah.
So,
You had the decaying.
so you could compare that to, say, the real instrument
Yeah.
and its waveform,
Yeah.
is what you're suggesting?
Take the oscilloscope and get the real
So,
waveform.
although that would help us tune for some instruments that have real-world equivalents, I think that the work she's doing right now with automatically generating the modes is going to be important for creating instruments that don't necessarily exist in the real world, and still having them be physically real, if that makes sense. So, like, no one has a brick xylophone, but there are sounds that a brick would generate, so.
Jim Anderson was playing the mugs at the Noah's flood over at University Methodist.
The ceramic?
Huh?
Are
Coffee
those-
mugs, hung coffee mugs that were pitched differently, and he was one of the 5 percussionists, and he was playing the coffee mugs.
Okay. I'm going to talk about the tablet implementation. So this was the first one we tried, and then we moved on to the multi-touch table, and it'll become clear why we moved on. So the Wacom tablets come with an API that can pass in the position of the stylus and the pressure and the tilt. And then using this information, we had the user use the styluses to play the instrument, and then we kept track of the position of where it was hitting. So pros, they're relatively cheap, $100 to $200 each. So more people could potentially play it. You could have distributed instruments everywhere. It's potential. The cons, and this is major, is that in order for the stylus to be recognized by the tablet, you have to hold the stylus at roughly a 90-degree angle. And you can sort of see that in this picture of the user using it. It's not quite 90 degrees, but you don't play very many instruments going like this. And so because of that, it totally takes away any intuitive advantage we have to working on this type of work. So we moved on, and we were lucky to have Renzi lend us this multi-touch table, and it's living upstairs, second floor G-Lab right now. I talked about it briefly before. It uses direct illumination, which is to keep track of where you're touching and how big your surface area of touching the table is. And so the way that works, I think, is the table itself knows where its light source is. So based on where the light source is, it can track where you're touching on the table is. So it can detect roughly 20 interactions. It depends on how you cluster them. It can detect more if you cluster it differently. And the API that they gave us allows us to track the IDs of the touch and then also keep track of the touch as it changes. So that's useful because if you're playing music, you can have multiple touches at once, which we could only keep track of 2 on the Wacom tablets. And so that means you can potentially have someone playing the xylophone with 4 mallets and doing things that real xylophonists do. So another advantage of the fact that it uses direct illumination is that you can use either your hands or a mallet or really anything as long as it touches the table to play any instrument. So in this picture, I'm using mallets, but if you were going to play the drum, you could use your hands, or when I do demos, I often get the middle schoolers we're demoing to play with their hands, because then there's not enough mallets to go around anyway. So. Sorry? I'm not sure. So these mallets, I didn't think I'd have time to go into what they're made of, but they're made out of cat toys. They're really deformable and soft. So they're not real mallets because those would actually break the table, or I'm afraid they would actually break the table. So I'm going to show a slightly longer clip of 2 people playing music on the table. So I wanted to record a slightly more musically complicated demo sometime this week, but then I got tonsillitis, so. And if anybody thinks that they could do a better job than that, you're free to come talk to me. I'd love to have you play for me. Okay, so we did a very small, I don't know if it even qualifies as a user study if it's 6 people, I guess preliminary pilot study, just to confirm the results and see what other people thought of it. And we only did it for the xylophone and not the drum just because of time constraints. And so we asked them 2 questions. We asked them, how easy was it for you to figure out how to make sound? And so what I did is I left them, I started the application and I left them there and came back 5 minutes later. And then they answered the question. They answered on a scale of 1 to 10. Where 1 is not easy and 10 is easy. And the second thing I asked them was I played them a clip of a real xylophone, so a physical xylophone, and then I played them a clip of the synthesized xylophone playing the same thing. And in case you're curious, I played a chromatic scale and then I played an F-sharp major scale, if that means anything to you. And I asked them how similar the 2 clips sounded. And these numbers are a little bit meaningless because there's only 6 people, but you can see the numbers. And we'd really like to do a larger user study in the future, and just with more people and probably more complicated questions, but there were time constraints with this one. So in summary, if you don't remember anything except for the funny videos and the fact that I took a long time to set up, is physically based sound synthesis in combination with touch-enabled hardware gives us really cool virtual instruments that have both the flexibility of digital instruments in terms of sound creation, but also all the intuition of traditional real-world instruments. And I have lots of ideas for future work. So obviously more instruments would be nice. You can model strains and you can model strained instruments. And there's cool percussion and stringed instruments like a hammered dulcimer, which are neat. And very soon, I'd like to work on a GUI for switching between materials very rapidly, just to make it easier for a normal user to switch between materials. A distributed percussion ensemble. Renzi has other tables that look alike in other locations, and it would be cool to do that. Just have people playing a piece of music together in different locations. This is the type of work that I feel like as soon as I mention to someone, everybody else has an idea of where it could go as well. So I guess I'll open up for questions as well as suggestions for future work now.
Thank you, Maggie. Additional questions?
So for your percussion instruments, you talked about switching materials of, like, say, bars and xylophone. Have you thought about modeling the material of the mallets and changing the sounds based on that?
So currently the only sounding object is the bars and not the mallet. And I think that in order to model both, although that would be really cool and obviously really useful in a lot of ways, would require changing our current pipeline a little bit.
How expensive is a multi-touch table like that compared to an actual xylophone?
Bam. I actually was told once and immediately forgot, probably intentionally, how much that multi-touch table cost for them to build. Do you know, Ming? Like, off the top of your head?
They have built a Renzi. My understanding is that they build a table to be really robust so they can move it around to a trade show floor. They use the best material and they really use the best metal, whatever. And the labor and everything combined together because it's built from scratch. It has camera underneath from 4 different corners. And it has very high resolution camera. So I think my understanding is somewhere around $20,000 inclusive of everything. But they say they can definitely build a lot cheaper. And there's also, that's including also the PC in there.
So my estimate for a real-life xylophone is probably around $500, $1,000 maybe, if it was a nice one. That's just my estimate. It's probably pretty accurate. But I mean, you can do so much more.
For the record, there are homebrew designs for these multi-touch tables that are in that range. So.
Thank you again, Maggie.
Ignore.
I understand what it says.
Okay.
So Calvin will talk to us about space.
Is this the
I think it might work.
pointer?
Push it and see if it works.
Negative. Do you guys just use the mouse? Okay.
Really well.
Yeah, keep arrow keys or the space.
Okay, great. Where's the camera?
You.
Okay, great. Good afternoon, everybody. My name is Calvin Young, and I'll be presenting my project today. It's called SPACE, short for Spatial Cluster Enhancer. And this is a novel algorithm that we've developed to solve the problem of graph classification based on mining for discriminative spatial clusters. I'm breaking down my talk today into these following sections. First, I'll be giving some background information, offering some definitions. I'll branch into some related works, and then describe our contribution. Then I'll talk about some of the experiments that we did, and then I'll offer some closing remarks and some future direction. So to begin, let's provide some relevant terminology. Graphs are data structures that can represent vast quantities of data as a set of nodes connected by a set of edges. Nodes and edges can each have different labels, distinct labels, in order to distinguish between the different types of objects and relationships within the data. Edges can also have different directions. If edges in a graph have directions, then we say that the graph is directed. Otherwise, we say that the graph is undirected. The edges that have directions symbolize different relationships that are asymmetric within the data. Our algorithm can function both on directed and undirected graphs, but for the sake of simplicity, this presentation is only going to cover undirected graphs. So in this manner, we can use graphs to represent both a variety and vast quantity of data. For example, if we were to represent the social relationships in basketball, then we can have a graph that looks like this, where the nodes represent prominent figures in basketball and the edges represent the different types of relationships within the figures. One of the key ideas to this problem is that in many applications, the structure of the data is related directly to the behavior. So when we abstract data into graphs, the structure of the graphs can tell us a lot of information about the behaviors that the graphs exhibit. On the left, you see a ball and stick figure of a molecule. Here, the atoms, we abstract the atoms as nodes in the graph, and the different types of bonds, the covalent, ionic, single, double bonds, as the different types of edges. Now, the structural information of the molecule is preserved in the graphs, and therefore, by examining the graphs, we can find about a lot of different information about exactly the different types of behaviors they exhibit. On the right, you see a ribbon structure that represents the backbone of a protein. More specifically, this is a mouse antibody binding to a carbohydrate antigen at the top. The ability for this antibody to bind to the antigen is directly governed by the shape of the binding site. Now, in the context of graph classification, why this is interesting to us is the shape of this binding site is an interesting pattern that we'd like to study. That is, we can use this pattern as a feature in order to discriminate between graphs that can bind to this antigen and those which cannot. So to proceed, let me first offer some definitions of what a pattern is and how it's used in this problem. A pattern is essentially any type of subgraph that can occur with some frequency in a graph set. So here we see two patterns, A, B, and GD. Now, if this is our graph set, then we see that graphs P1 and P2, as we see that pattern A, B is expressed in graphs P1 and P2, and pattern GD is expressed in graphs P3 and P4. An occurrence of a pattern is simply an instance of a pattern in a graph. And if a pattern has an occurrence in a graph, then we can say that the graph supports the pattern. So for example, graphs P3 and P4 both support pattern GD. Carrying the example of pattern GD even further, we define the notion of pattern frequency. Pattern frequency is defined as the ratio of the cardinality of the set G prime divided by the cardinality of the set G, where G prime is simply the subset of the graph set that supports the pattern, and G is the total graph set. So in this example, pattern GD has frequency 2 over 4 or 1/2. Each pattern can, in order to evaluate how effective the pattern is in discriminating graphs between the positive and the negative set, we offer the definition of a discrimination score. The discrimination score of a certain pattern is defined as follows, where as the log of the frequency of the pattern in the positive set divided by the frequency of the pattern in the negative set. The reason why we use this definition is because we want the discrimination score to increase as the pattern's frequency increases in the positive set. We'd also like the discrimination score to increase as the pattern's frequency decreases in the negative set. There are two cases in which this discrimination score is relevant. One is if the pattern frequency in the positive set, f sub p, is equal to 0. In this case, we don't even consider the pattern because if it's not frequent in the positive set, then it bears no interest to us. The other case is if f sub n, the frequency in the negative set, is equal to 0. In this case, we can either replace the value f sub n with a value very close to 0, or we can add in a negative graph that has every occurrence of every pattern. Both of them yield the same effect. With these definitions in hand, we can provide a more formal description of the graph classification problem. The graph classification problem takes two data sets, a negative set and a positive set of graphs. And the goal is to train a model to discriminate and classify an anonymous graph between one of these two graph sets. The positive set generally contains graphs that exhibit a certain characteristic of interest. For example, in the last example, antibodies that can bind a certain antigen. A lot of the characteristics that we study in the positive set are characteristics which are governed directly by the structure of the graphs. It's common for the graphs in the negative set to be both more diverse and more numerous than those in the positive set. The problem of graph classification has found application in a variety of different fields. For example, in pharmacology, it's being used to detect which compounds are toxic and which are not. In drug development, it can be used to automatically detect which molecules bind a certain ligand and which do not. And in software engineering, code blocks can be abstracted into nodes of graph, and program flows can be abstracted into edges. And the problem of graph classification can detect anomalies in program flows. Early works in this problem noticed that certain frequent subgraph patterns can serve as good classifiers for the graphs. That is, if subgraph patterns occur more commonly in the positive set, then they should be good classifiers in order to distinguish whether a graph it belongs in the positive set. So the workflow for these algorithms is they first mine for frequent subgraph patterns. And then they filter these subgraph patterns, taking the entire pattern set and filtering out those which are frequent in the positive set, and then further filtering out those which occur infrequently in the negative set. And then they convert all the graphs in the positive set into feature vectors. So for example, if this is the pattern set that is returned by the first two steps, then we can convert this graph into the feature vector 1, 1, 0, where a 1 represents the presence of a certain pattern and a 0 represents the absence of a pattern. Finally, converting all the graphs into feature vectors in this manner reduces the problem to simply classification of high-dimensional data points, which can be accomplished with tools such as support vector machines. But there are several known problems with this method. First of all, while this method is good for small graphs and small data sets, as the graphs increase in size and as the data sets increase in size, we get an exponential blow up of the pattern space, which both makes feature selection very difficult and makes removing redundant graphs from the sets very difficult. This is a huge scalability problem, and pattern mining under this method normally becomes the bottleneck. The explosion of other methods to solve this problem in recent years have taken a variety of different approaches. For example, many boosting algorithms have been developed where they assign weights to certain graphs, and then they iteratively and incrementally form a pattern space where during each iteration these algorithms adjust the weights for each graph and increase the weights of those graphs that are either misclassified or unclassified by the current pattern space. Another recent algorithm, GPLS, uses a powerful mathematical function called partial least squares regression in order to extract latent features from high-dimensional data points. But these latent features have the known problem of having poor interpretability. Another recently developed algorithm, Quark, uses a submodular scoring function rather than the heuristic scoring function, the discrimination score that we defined earlier, in order to calculate the discrimination power of each of its patterns. A known feature of using a submodular scoring function is that when used in conjunction with a greedy forward selection in order to choose features to be included in the feature set, this yields near optimal results. The problem with this is the runtime is horrible, and on some data sets it will take hours or even days to complete. Our contribution to this problem is based on the observation that subgraph patterns which occur in co-occurrences with one another form natural spatial clusters. For example, these two figures show two proteins where the blue ribbons are the structure of the protein and the red spheres represent the nodes in each of the patterns. These are several different patterns that we found using another algorithm that we developed, and what we see is that these patterns form natural spatial clusters. These patterns forming spatial clusters can represent, for example, different features in the same active site or the same binding site in this example of proteins. Exploiting this observation, our goal is to develop a graph classification algorithm that exploits the natural formation of spatial clusters to mine for and so we mine for discriminative spatial clusters in order to assess the feasibility of using this as a method of classifying graphs. The algorithm that we develop is called SPACE. It is Spatial Cluster Enhancer. The basic idea of this algorithm is that we first mine for subgraph patterns, and then we group the patterns occurrences from each graph in the positive set and expand them to form spatial clusters. Once we've formed these spatial clusters, we use these as input into the subgraph mining algorithm again, and iteratively refine these algorithms until the spatial clusters converge. One of the key things to note here is during the mining stage, in order to leverage the information that patterns which form spatial clusters also occur in co-occurrences, we need to employ a subgraph mining algorithm that actually mines for co-occurrences. In order to do this, we use a pattern mining algorithm we've previously developed called COM, Co-Occurrence Miner. Several of the key features of this algorithm are that it uses a canonical coding method to represent the patterns. That is, it can represent each pattern uniquely, and this allows us to create an efficient pattern exploration order in which we explore the pattern space efficiently without repeating any patterns that we've already visited. The end goal is creating rules based on these co-occurring patterns that can discriminate between positive graphs in the positive set and the negative set. What we find is that this is a much faster algorithm than traditional algorithms, and it also offers very competitive classification accuracy. So the basic workflow for the COM algorithm is as follows. COM maintains 3 major data sets. One is the pattern heap. The pattern heap organizes all of the currently explored patterns and orders them by individual discrimination power, so that the pattern at the very top of the heap has the highest individual discrimination score. The candidate co-occurrence list stores all of the co-occurrences that we've currently generated which have not yet been inserted into the final rule list. So during each iteration, we take the next pattern from the pattern heap and compare it with all the co-occurrences in the candidate list. And then we find the co-occurrence for which the union of this pattern with that co-occurrence yields the greatest increase in discrimination score. Next, we insert this pattern as a new co-occurrence in the candidate list by itself. Then we take both of these new co-occurrences and we compare them with the rules that have already been added to the final rule list. If either of these co-occurrences allows us to discriminate positive graphs that have not yet been discriminated against with the final rule set, then we go ahead and add it to the final rule list. One of the key things to notice is after a co-occurrence has been added to the final rule list, the rule never changes. And this notion is very important. We're going to use this to explain why spatial clusters yields a different result than COM. Some of the experimental results for COM are shown here. The top graph displays COM's normalized accuracy, and the bottom graph shows its runtime compared to 2 other state-of-the-art methods, namely GPLS, which we explained earlier, and LEAP, which bears some resemblance to a boosting algorithm. What we see here is that COM offers very competitive and even significant classification accuracy for some data sets. But what's more significant than that is noticing that COM offers at least 1 order of magnitude greater runtime and time efficiency than any of the other algorithms, which makes COM a particularly viable option for us to use in our pattern mining algorithm, because since each individual execution of COM is fast, we can execute it multiple times, and our algorithm will maintain competitive time efficiency. So with that in mind, I will now I'll talk about the workflow that we've developed for space. Essentially, we start with a positive and negative graph set, and we invoke COM on this graph set in order to mine for frequent pattern co-occurrences. We then take a look at the subgraphs, the pattern co-occurrences, and look to see if they converge. If they don't converge, then we build a refined positive graph set using spatial clusters and use this as input to execute COM again. And we continue this process iteratively until the subgraph patterns converge. So here's an illustrated example of the space workflow. Suppose the graph on the right is an example graph in the positive graph set. And then suppose this is one of the pattern co-occurrences that are returned by COM. Since this is the first iteration, we can't say that the subgraphs converge, and so we continue to construct a refined positive graph set. Now the refined positive graph set procedure proceeds as follows. For each graph in the positive graph set, we construct a new graph that contains only the pattern occurrences that were found in that graph. And then we iteratively expand these occurrences to include all nodes and edges that occur within a d distance of the occurrence. The distance can be defined in multiple ways. In molecules and proteins, our edges actually represent distances, so you can expand them by distances in units of angstroms. But for the purposes of simplicity, here we're just going to expand the nodes and edges by node hops. So if we expand these occurrences by 1 node hop, the resulting graph looks something like this. And then if we expand it by 2 node hops, the resulting graph looks like this. We perform this operation on every single graph in the positive graph set while leaving the graphs in the background graph set untouched. And then we use this new transformed positive graph set in the original background set as input into COM again, and continue mining after we've identified these hotspots, continue mining for more pattern occurrences until we find some subgraph patterns that converge to a certain result. We invoke COM again, and then if it doesn't converge, then we report this as the final result. In order to test for the convergence of these subgraph patterns, we proceed by taking the following steps. We iterate through all of the rules in the rule set generated by COM, and within each of those rules, we iterate through all of the patterns and add them to add all unique patterns into a pattern list. We then sort these patterns by their CAM code, which is the canonical adjacency matrix code. The CAM code offers a unique encoding method by which we can uniquely identify all the patterns, thereby making the sorted order of patterns unique. And then we test for the convergence by looking if the convergence score falls below a certain threshold value. The convergence score is defined below as the ratio of the edit distance between the previous sequence of patterns to this new sequence of patterns divided by the size of the previous sequence of patterns. This is effectively the percent change between the two sequences. The edit distance can be calculated in a number of ways. In this particular implementation, we use the Levenstein distance, which, because the two sequences can have different lengths, the Levenstein distance is defined as the minimum number of transformations to the minimum number of edits to transform a sequence into a new sequence, where each edit operation can either be an insertion, a deletion, or a substitution. The experiments that we run fall into two sets. The first set of experiments, we use protein data sets, and here you see some of the attributes of each of these protein data sets. The proteins normally have about 30 to 40 graphs in the foreground set and 256 graphs in the background set. Each graph has, on average, 275 nodes and about 2,600, 2,700 edges. In the second set of experiments, we generate our own synthetic graph sets, and I'll go more into detail about that a little later. In order to evaluate the performance of our method, we use normalized accuracy, which is the average of the sensitivity and the specificity, where the sensitivity is the number of true positives divided by the number of true negatives, and the specificity is the number of true negatives divided by the number of total negatives. And what we see with the protein data is that when we compare the results of COM in space, space offers approximately comparable results to COM, where space yields marginally greater normalized accuracy for some of the data sets. From the runtime information, we see that space takes about twice as long as COM. This suggests that COM executes twice, iterates twice in the space workflow before terminating. Something to keep in mind here is that COM is at least an order of magnitude faster than other graph classification methods, so that even though space is twice as fast as COM, space is still almost an order of magnitude faster than other state-of-the-art methods. But since space didn't yield phenomenally better results for the protein data, we decided to examine exactly why. And we noticed that after we formed the spatial clusters and we expand the spatial clusters by 1 or 2 node hops, the spatial clusters essentially just degenerated back into the original graphs. So the next execution of COM was approximately equal to the original execution of COM on the original graphs, and thereby causing the algorithm to immediately terminate. In order to remedy this, we wanted to experiment with some synthetic data. In generating synthetic data, we needed to specify 4 parameters. Each of the base values of these parameters were taken from the values in the protein data sets. First, we need to edit the number of unique node and edge labels, the number of graphs in each set, the number of nodes per graph, and the edge density. The last 2 of these parameters are most important for our purposes. The nodes per graph represents the size of the graph. The edge density governs the sparseness. In generating these Ren data sets, we generate the foreground graphs with a limited set of node and edge labels, with a superset of these labels being reserved for the background set. Furthermore, in generating the graphs, nodes and edges in the same region are more likely to share common labels. In this manner, we generate the graphs such that graphs in the positive set are more likely to share common patterns. Not only that, but the common patterns are likely to cluster together, are likelier to cluster together in the background set than in the background set. And the idea behind generating synthetic data is that since in the protein data, after we expanded by 1 or 2 node hops, the spatial clusters essentially degenerate back to the original graphs. So we thought that if we made bigger graphs, then the spatial clusters might have more room to grow and have more room to be refined. The idea being that spatial clusters are more effective when they have more room to adjust. So we generated a synthetic set of very, very large data. These nodes contain these graphs contain about 1,000 nodes, and they have an edge density of about 10 edges per node, which is comparable to those in the protein data set. But what we see is contrary to our initial thought, space still yields very nominal, very marginal increases over COM, and the runtime stays approximately the same. The reason for this is, although the number of frequent patterns found by COM is only marginally higher, the number of occurrences of each pattern in each graph increases significantly. And so because of the denseness, and because we have so many occurrences, once we expand the spatial clusters by 1 or 2 node and edge hops, these spatial clusters once again degenerate back into the original graphs. The reason, again, is because, one is because the graphs are so dense that when you expand by 1 node or edge hop, you capture more of the neighboring nodes and edges. The other reason being the diversity. As we generate the graphs, the internal structures of all these large graphs are fairly homogeneous, and so whenever we find one pattern, the pattern has high likelihood of occurring many times in the same graph. So this leads us to another idea where, rather than expanding the graphs themselves, we generate sparser graphs. These are the results. We generate graphs that have about 275 nodes, which is comparable to those in the protein sets, and graphs that have an edge density of about 4 edges per node. And we see that that space yields, on average, about 3% or so increase over COM, which is good for our experiments. The reason this is so is because with sparser graphs, we have the same number of occurrences in the graph, but as we expand the spatial clusters, they don't expand as quickly. Having fewer edges between nodes effectively increases the distance between each node and an arbitrary occurrence. And so the spatial clusters essentially have more room to grow and more room to be refined. To take this one step further, we compare the increase in normalized accuracy with varying edge densities, with edge density of 10 being the edge density of the original protein graphs and edge density of 2 being an edge density that quickly approaches paths. And we find that edge densities between 4 and 5 have the greatest increase in normalized accuracy as a result of the spatial clustering. We find that with an edge density of 2, the normalized accuracy increase dips down because with each expansion of the spatial cluster, we are able to capture less and less information. And with less information, we have less room for the data to actually be refined. So to close, we found that spatial clustering does show promise in terms of increased accuracy as a method for graph classification, and that spatial clustering yields greater improvements in moderately sparse graphs. In the future, I'd like to take a look at different characteristics of graphs in which spatial clustering might be more useful, particularly graphs that are more diverse, that is, graphs that have different internal structures that discriminate one another. I'd also, if possible, like to find more organic data, as this would be a better representation of what the algorithm does. We'd also like to develop an algorithm that mines directly for spatial clusters rather than taking this iterative approach where we first mine for co-occurrence patterns, expand the spatial clusters, and then continue. We expect this to have greatly improved runtimes and perhaps even marginal improvements in accuracy. With that, I'd like to thank Ning for his help in developing the original COM algorithm. I'd like to thank Dr. Wei Wang for her infinite support and mentorship these last few years. I'd like to thank Dr. Kevin Jaffe and Kelly Gaskell and everyone else in the organizing committee for giving me this opportunity to present my work. And with that, I'd like to open the floor for any questions.
Thank you, Calvin.
Question for Calvin.
I guess I don't understand how you can guarantee that either COM or space terminate when you're...
So the workflow for COM, whenever we add a new co-occurrence to the rule set, we do so because the co-occurrence can discriminate new positive graphs that the current rule set can't. And the algorithm terminates once the rule set can discriminate all of the patterns in the positive graph set. Is that there's no more discrimination to be done. Does that make sense?
I guess, couldn't there always be more patterns, or are we starting with?
No, because, well, so the idea is a pattern discriminates, a rule can discriminate pattern, a rule can discriminate a certain graph in the positive graph set if the graph exhibits all of the patterns in the rule. So if all the patterns in the rule are occur in the graph, then we say that with absolute or with predicted certainty that the graph is in the positive set.
Okay.
Does that make sense?
Yeah.
Okay.
You mentioned spatial clustering as providing significant advantage here. I'm wondering to what extent this is related to the problem, because you're trying to discriminate geometric differences in the graph where edges are different distances. You mentioned software, like looking for anomalies. There it may be the case that in terms of the graph, things are very far apart.
Yeah, so the spatial clustering will have significant advantages with data that exhibit natural spatial cluster patterns. So in the case of program flows, it might not be as useful. Where this is the example that we use is proteins, because in proteins, the active binding site is what governs the behavior of the protein. And rather than and a lot of these algorithms can't find every single pattern in the active binding site. Rather, we find different features that are part of the same active binding site and use that in order to discriminate the functionality of the protein. This might not be as useful in, for example, chemical data, where where chemical data doesn't exhibit the same type of spatial clustering. Okay.
So one more question.
Sure. Yeah.
So you can find some features that you're looking for. If you're also looking for the absence of some features, is that fit in the scheme? You have negative examples where
we only mine for frequent patterns in the positive graph set, and as a result, there was another algorithm that we developed that also mined for patterns in the negative graph set, but I don't believe that. And you might be able to help me out here. It doesn't yield as great increases in normalized accuracy.
Other questions?
Would there be any way to intelligently determine the degree to which you want to expand a pattern per iteration?
So in order to, in our experiments, we experimentally expand the graphs a certain number of distances with each invocation of the algorithm. In order to actually determine an optimal solution, I'm not entirely sure. That hasn't been figured out yet. The best that I can do right now is estimate, or rather explore the feasibility of using this as an approach for solving graph classification for data that exhibits natural spatial clustering behaviors.
Well, thank you again, Calvin.